All right, I think we'll get started. Okay, everything is turned on. I'll start with a couple of administrative things which could have turned very ugly, but we managed to make them only modestly ugly. So a week from Thursday, I will not be here. I will be in New Mexico for another obligation. So what we have done is we've rescheduled the class for the following Tuesday, 9:30 to 11. That'll be the update, or the makeup. Of course, those of you who are not inclined to or not able to come from 9:30 to 11 can always watch the video. Now, the problem is that the following Tuesday, which is the 19th, this room is in use all morning. So on the 19th, we will move class to 306 SOTA, which is the big lecture hall on the third floor of SOTA, which has the same video facilities and is available from 9:30 to 12:30. So I will post all of this on Piazza after class, but the major logistical moves are no class on the 14th, and then makeup and regular class 9:30 to 12:30 on the 19th in 306 SOTA. Good. All right. Any questions or comments? All right. So what we're going to do today is really get to the point, or close to the point, where we can actually do something interesting, or at least do something. So I'm going to talk about the lead up to the first programming assignment, which is the structured grids assignment. And then I'll spend about half the lecture talking about GMake and kind of in the process teaching you about some of the things that, how one actually does things in C++. So, so first let's talk about structured grids. So there's a picture right here of a nice structured grid. It's numerical solutions of PDEs or other spatial problems are represented on a hierarchy of nested rectangular arrays. So you have, here's the rectangular part of this, kind of the white lines show you where grid lines are. And at every intersection of every three grid lines, you have an unknown, or more than one unknown. Here's the hierarchy part, which we won't really talk that much about in this class, other than to motivate why we're doing things the way we do, which is that you can have different levels of refinement. So here's a region. The region in three-dimensional space is organized into blocks, which are indicated by these black wire frame lines, and it's nested in the sense that the grid lines are integer submultiples of the spacing of grid lines is an integer submultiple of the next coarser level. So this is typical of a lot of calculations with spatial models, and in particular for partial differential equations. And that's going to be the focus of, implicit focus of what we're talking about here. Because what we do is we look at what kinds of calculations we do, and we see that there are local stencil operations on rectangles corresponding to either explicit methods or iterative solvers. Typically, you have to do something irregular on boundaries, whether it's on a domain boundary or on a boundary like this between different levels of refinement. You often have to copy between rectangles. Now, this looks like a very specialized setup. Well, it is for this kind of multi-resolution hierarchical calculation. But even if you were on a uniform grid, but performing these calculations on a large-scale distributed memory parallel computer, you would want to break your domain up, even if it's uniformly gridded, into chunks, into rectangles, and deal them out to processors. And at that point, you're talking about, well, how do I orchestrate or choreograph, in Paul Hilfinger's term, the data movement between, between different processors and between different rectangles. So what else do we know about this algorithm space that informs the way we go about things? One thing we know is this is order 1 flops floating point operations per memory access. So that means you have, you know, tens to hundreds of floating point operations per word accessed from memory. It's a very regular calculation. On a rectangular grid, we can arrange things to do a lot of stride 1 data access, but we have a certain amount of irregularity on boundaries between, on boundaries. So that's a so-called codimension 1. Codimension's a fancy math term for talking about things that are one dimension, however many dimensions lower. Codimension 1 is 1 dimension lower. And that's typical of the kinds of irregularities you have to deal with. Now what? Don't do this. Thank you. So another aspect of calculations using this is what you might call multi-physics complexity, that you have a lot of different operators acting in sequence on the same collection of state variables. The operators themselves may contain state for performance reasons. This fact here, that you're constantly applying operators to the same data over and over again, is kind of what broke the pure object-oriented approach to doing things, because the operators had a life of their own. They might be applied to different data. The data has a life of its own. It gets applied to different operators. That's the way you need to factor the software. And then the other thing is that when you look at these sorts of things in the context of parallel computing, that your irregular computation is typically combined with irregular communication. So that makes it harder to do parallel. And those of you who take CS267 will see exactly what that means. So here's a simple example, and this is going to be the example you'll work with in the first assignment. So we're solving Laplace's equation on a unit square, or solving Poisson's equation on a unit square. So we define Laplacian, which is the sum of second derivatives in each direction. And in fact, the way you'll implement this is that you won't be able to tell the difference between 1, 2, or 3 dimensions. You discretize this using finite differences, that you replace your continuous space by a grid of n by n, or n by n by n lattice points. And the values of phi on those lattice points are intended to approximate the solution at the continuous points corresponding to those lattice points. Finally, we have the definition of the discretized version of Laplacian. And the way you get that is we just take these derivatives and replace them by center differences and sum them all up. So it's 1 over h squared, sum of all 4 nearest neighbors minus 4 times the place where you're evaluating the operator. As an operator, what does that look like? Well, it looks like, in our case, something that maps a box, but a box that's 1 smaller in each direction. So instead of going from 0 to n, it goes from 1 to n minus 1, because you need these extra points on the boundary to be able to evaluate the operator. So you have regular data access, lots of stride 1 access if you set it up correctly. It's also easy to figure out who your neighbors are. You know how to, if you've defined what this domain is, kind of mathematically, you know what directions are up, down, left, right. The mathematical properties of these discretizations are well understood. It's the oldest form of numerical computing, actually goes back to prior to the existence of electronic computers. Okay, so how are we going to represent this? Well, the natural way to represent this, coming back here, would be to think of our solutions as being multidimensional arrays. That's kind of the way we've written them, is phi ij is an array with indices in multiple spatial directions. The problem is C++ does not have multidimensional arrays with runtime specification of dimensions. We can define a multidimensional array, but we have to know what its dimensions are, 5 and 4 for a two-dimensional array. We have to know that it's 5 by 4. And that's not convenient in almost all cases, and it is definitely not convenient if you're doing things like parallel computing, where you deal out patches to processors, or you're doing things like adaptivity. We want to build a C++ class to provide us with that feature, specifically for use in rectangular grid discretizations of PDEs. What are some of the things we're going to try to do? We're going to try to make memory management automatic. And the way we do that is just by making sure the constructors and destructors are defined correctly. There's going to be some attempt to make things modular and to separate concerns so that you have a lot of machinery, what looks like a lot of machinery, but it's once the machinery is built, you don't have to think about it. In fact, you'll be handed a lot of the machinery to start with. And then we're kind of implicitly anticipating generalizations to unions of rectangles. And then finally, we'll enable implementations that are independent of dimension, in the sense that if you specify the dimensionality of the problem at compile time, then you're done. Why is this useful? Well, for one thing, if you're doing lots of different applications, some problems in 1D, some in 2D, some in 3D. In fact, we've gone as far as 5 dimensions for phase space problems for plasmas. It's nice to be able to debug components in a lower number of dimensions and have some reasonable expectation that they will continue to work at high dimensions. And in any case, if you are doing problems in lots of different space variables, multiple space variables, you don't want to have to maintain multiple versions of the same code. So all this. So here's how we're going to represent data on a rectangle. So it's going to be a templated class. The class template is going to be the value that arrays take on. So in this particular case that we showed for Laplacian, that would be either float or double. So T would be one of those two. But you could certainly have rectangular arrays of ints and actually rectangular arrays of even more exotic things. Now, I'm throwing in one other thing that we won't use on this assignment, but we will use later, or at least you'd want to have there, which is, but it's a good example of another feature that you have in generic programming for in C++, is that you can have types that are parameterized by other types, by a class, but you can also have types that are parameterized by integers, by integer literals, numbers. So, and what does this number stand for? Well, this stands for, if you want to have, instead of a real valued array, you want to have a array that represents vector velocities. So it'd be a 2 or 3 dimensional, 2 or 3 component array. You can actually specify in this type the dimensionality, provided you can specify it at compile time. So you'll see how that works later. And in fact, you're specifying both of these at compile time. When you actually use rectMD array, you are using it for these parameters being known when the compiler hits the code.
So providing n not equal 1 basically
Yes, for integer literal template template parameters, you can give them a default value. And defaults work kind of from the outside in. If I had multiple integer ones, as I might have had if I wanted tensors, for example, you can default the first one and not the second one, but you can't default the, I'm sorry, you can default the second one and not the first one, but you can't default the other way around. You can't default the first one and not the second one. It should be able to tell which one is defaulting simply by counting how many arguments it has there. So what's in the class declaration? A bunch of member functions. We'll talk about those in a bit. And what's in the data members? Well, you have a box. I'm calling it dbox because this is actually code that I'm having interoperate with another closely related set of things that already took the variable box. So I'm avoiding a namespace collision, and I felt that this was just adding namespaces to this was just too heavyweight. So I made a new box name, and it's not just that it's a new name, it actually has slightly different semantics, and I'll actually talk about that. So what's a box, though? A box is that range of indices. So remember I had back here the range of indices over which my arrays were defined, whether it's phi or the operator applied to phi. That is a first-class object. That is a defined type in our programming system here. The type name is box, and here's an object of type, or the type name is dbox, and here's an object of type dbox. So in addition to that, and so that's how you define how the indices are defined. And now in addition to that, you have t star of m underscore data. That's a pointer to what will ultimately be a contiguous block of data that will be that you will allocate using the memory manager, using new. Now, so in order for this to be useful, I have to define what a box is. So let's kind of go down the rabbit hole. So here's class dbox, bunch of member functions here. And how am I going to define it? I'm going to define it in terms of a lower left and upper right corner. So here we have m underscore low corner. It's of type point. What's a point? We'll get to that in a moment. And low corner is, so for example, in that first example we had, our low corner would have been 0, 0. And what's the high corner? Well, the high corner is NN. If you specify the low and high corners, you've specified a rectangle. So that's what, so now I've specified box in terms of point. Well, what's a point? Well, point, bunch of member functions here. Now, we have data members for point. By the way, these were the data members. By the way, you know, so m underscore low corner, m underscore high corner are things that box contains. Now, what are the things that point contains? Well, now we're down to something where we're no longer defining it. It comes from somewhere else. So it's in the standard namespace. It's array. So this is another STL class. So we have arrays of, it's a templated class with two template parameters. One is a type, and the other is a integer. So what is that? It's an array of length dim. Now, the rule for these kinds of arrays is the rules for arrays in ordinary C, that dim has to be a compile time constant. So somehow we're going to have to propagate dim into this and have it be 2 or 3. But now from here, everything is known about array. It has a set of rules, and we can use that. And they're pretty much the rules of ordinary one-dimensional fixed-length arrays, except for a couple of things. One of them is that these are really, as I said, these are real types. Arrays, C arrays are not quite real types. They can't quite do everything. So it doesn't make sense to talk about a reference to a C array as an aggregate thing. So this now makes, C arrays real types to which we can do everything that we can do to any other type. So now that gives us, so now we're done. We have point, we have box made up of 2 points which define the corners, and then we have rectmd array, which is a box and the data put it in. So why did we do it? Why did we make separate classes for point and box to represent the range of indices? Well, for one thing is that it facilitates writing dimension-independent code. The dimensionality is a parameter, maybe set at compile time, but other than that, you don't have to worry about it. operation, and you'll see later that there are going to be operations on arrays that will be stated in terms of box and point without respect to dimensions. So another thing is that operations occur on subsets of a grid. If you start out with an array of phi, which goes from 0 to n, squared or cubed, now the operator only is applied to something on one smaller. It should be easy to construct that and to distinguish between the two kinds of operators. Plus, you need to set boundary conditions for the operator. It should be easy to express that. Applying operators to subsets of boxes is, these subsets can be computed using functions on box, and this is so-called set calculus. And as I said, this is one of the things that you would express. There's kind of a parallel universe above box where you're talking about unions of rectangles, where now you have a separate first-class object, which is the rectangles on which they live on. And those would be a collection of boxes. So now let's look at a program. And this is a program that you'll get as part of the first assignment as a template for what you need to do. There are parts you're not going to get, and I'll tell you what those are in a moment. So this is MD array main. It's a C++ main program. Here is, I have an include IO stream. So here's another STL or STD, standard namespace file to give me some nice IO. And then I have the header file for rectMD array, and that's rectMDarray.h. So here's main, the usual main. We have declare points to be low corner and high corner. So these are actual points, and now we have to set them. So we set them outside as points. And how am I going to do that? Well, now we see an example of something that makes I/O much easier than using printf, which is cout. And I talked about that a little bit last time. So we're going to send to standard output, terminal output, a string, which is input size in each direction, parentheses and quote, and then it says now I say dim, so I'm going to output whatever the dimensionality of the problem is, ints, and then end line, which is that there shouldn't be a backslash there. It should be just, no, I'm not even going to try to fix that. Fix it later. Okay, so now we know how big we have enough information to, or we've asked for the information. We've written out to the terminal, enter these numbers, please. And so it's assumed that they're entered, and now here's how you get information in. Here's an input stream, cin, and that comes from standard input from the terminal. And I'm inputting cin. I'm looping over all the dimensions, all the directions. I input an integer, and this should have been reset to, when I edited this, shouldn't be size, it should be length minus 1. Our high corner is length minus 1, our low corner is 0. So that gives me a grid of size, length in that direction. So now I have points that are, high corner is whatever these three integers have been entered, and low corners are all 0. I've also now set a mesh spacing h, which is 1 over the number of points in the 0th direction. Now I finally can define my box. I have dbox has a constructor. It takes 2 points, low corner and high corner. And it's the obvious, and it creates a box with the obvious low and high corner. Now I can define, so this is the box over which my solution, or my phi is defined. I can now define a box over which L of phi is going to be defined. It's d0 and it's d, and I have a function called grow. Grow can take integers, either positive or negative. And what grow does is that either if the argument is positive, it grows the box by that amount. If the argument is negative, it shrinks the box by that amount. And then finally, I can define my rectMD arrays. It's rectMD array double. If I had more than one component, I would have to put an integer here, but the default value for that integer is 1, so now I'm just getting a scalar rectMD array for a phi of d, and then a scalar rectMD array for L of phi of d0, just defined on the smaller box. So here's the next piece of main. I got it. I wanted it to do something. So what do? I'm going to walk through all the points in box. And to do that, this is a standard C loop syntax. I have for my initial pass through the loop, I say P is equal to the low corner of the box. I say I'm going to quit if P is equal to the high corner of the box. I will continue to do this if P is not equal to high corner of the box, and then I will increment P. Now, increment is a member function of D, of box, or D box. So D box has enough information that given P, it knows how to increment it by 1. That's all you have to know about it. So here I have vals equal to 1, and essentially what I'm doing is I'm setting phi of P to be the product of signs, sine 2 pi x, where x is the index times is the vector of indices times h. Easy enough. Now I'm going to evaluate L of phi on this. I start out with P is at D0 of low corner. Note I'm using D0 here, not D. So I'm only going to evaluate L of phi on points where it's defined because I know that that's the right domain. That's how I've set things up, and it checks all of that for me because I've been modestly careful about how I define things. So P starts out at low corner. P is going to go until P, as long as P is not equal to high corner, and at that point it quits, and then we increment P. L of phi is equal to 0. So now I'm going to, so for each point, I initialize phi to 0. I add to the point phi of P plus the unit vector in this direction and phi of P minus the unit vector in that direction. And then I add to it the diagonal term and divide by h squared. And that gives me L of phi. So, a couple of questions you should be asking. Where did dim come from? Well, at the top of point.h, I included the following statement. Sharp define dim 2. And so prior to compilation, what happens is that the C preprocessor replaces every occurrence of dim with 2, provided you have point.h in the header there. We'll get to where point.h came from because all I have here is rectMD array.h. So where did point.h come from? I'll show you in a minute. One other thing you can do is, this is an easy way of managing dimension independence. You can set this at 2 or 3 or 4, whatever you choose, and recompile. In addition, you can override this in the compile line. If you say, I'll show you the command in a bit. If you say minus d dim equal 4, then the compiler will ignore whatever is in these defines and replace all occurrences of dim with 4. Now, there are lots of things that look a little clunky here and also look like they're performance problems. We're recomputing where to look in our rectMD array. Where to remember what we have is essentially a 1D array of data, and we are putting into that 1D array, we are stuffing into that some version of 2D array of data. And the mapping for that is typically just flatten. Here's one example. This is row major ordering. You have the flattened index to be P of 0 plus the difference between the high corner and the low corner times P of 1. So, and then that tells me where in data to get the data. So, and it's actually more complicated than that if you are if you're doing this in a dimension-independent way, a little more complicated. But it certainly doesn't look like incrementing by one along each row, and this has consequences. If this first certainly is more expensive to compute, but it also has consequences in terms of other performance opportunities. You know, we don't really know what order we're traversing the points. I've told you an order, but maybe it's not the one we're using. It's not part of the contract. How do we have function calls here, where this is, the increment is a function. What missed opportunities are there for optimization? If the compiler, if it sees a series of floating point operations with increment 1, it may be able to do something smarter than just, you know, compute each of them independently, for example, on machines with vector instructions. So there are various ways of managing at least some of the complexity. One is iterator. I'll skip that because we're not really going to use iterator, and in a lot of ways, it's not a solution that later on when we do the performance stuff, it's not the solution we will use. I leave it up here, though, because it's a common pattern in C++, is that you have iterators which are associated with iterating through something, and they all have the same syntax. You have begin, you have not done, and you have increment, and you have index into that structure, address into that structure. And it's its own class, it's its own type. It's an example of how you can abstract things away. Here's some other things that decisions we made. In the other version of box that I have that has to interoperate with this, boxes actually have centering. So you have a distinguish between boxes that are centered at where the open squares are. In 2 dimensions, so that's cell-centered. In 2 dimensions, you can have vertex-centered boxes, which are corner-centered, and you can have face-centered boxes. Why is that important? Because, for example, what it means to coarsen is different depending on these centerings, and also what it means to be nested is different depending on what these centerings are. Do you want to handle these by having to be an attribute of box or a rectMD array? In the other version, in the thing that this is talking to, these are attributes of box. So what other things have we done here? Do we have assignment operators? Do we have copy constructors? Remember, arrays are going to be pretty big things. Do we really want to, you know, say call by value on an array because you'll make another copy and that's a big copy? The way you keep that from happening is you make copy constructor private. Then no one can do that. So you will be forced to call by reference. You won't even do it by accident. You'd also might like to have a richer set of operators. You might want to have algebra of operators. But again, there's going to be lots of redundant copying of data. This kind of algebra of operators is why MATLAB is so powerful. It's why it's so easy to program in. But it's also why MATLAB has such dreadful performance characteristics when you just use this interface, because it's constantly making copies. So for large objects, this can lead to a lot of memory bloat that's neither obvious nor easily controlled. So that's one other design choice, and then we'll leave the design things and go on to GMake. This is a kind of one of these things that's there are strong opinions about, and I'm no exception. For class design, one thing that is very much people prefer to have is strong construction. That is, strong construction is where at the point you declare, you actually have a complete definition of the class. So in rectMD array, you would have, this would say, the only kind of construction we're going to allow is a constructor that takes its box argument. Because once you know the box, you know how to allocate memory for it. So that's strong construction. Everything is allocated, it's ready for use. Now, when a default constructor, this is rectMD array psi, and then you have the opportunity with a default constructor, and in fact you have to with a default constructor, define what psi is by applying a member function called define that finishes defining it. So this looks like, you know, this looks like a really petty sort of distinction, but it's not. And the place where you see where it's not petty is if you try to make aggregates of things. So let's say you wanted not just a single rectMD array, but an array of length 5 of rectMD arrays. Here's how you would do it using default and define. You would have rectMD array foo of phi, and each one of these would implicitly call a default constructor. So now you come down here, and now you have to finish defining it. Phi of 0, define B array of 0. So you'd have an array of boxes, and you would call phi, you would call phi define with those boxes. What's the alternative? The alternative is to use an array of pointers. So if you have strong construction over here, what the only thing you can really do is to use an array of pointers and use new. So rectMD array of foo star gives you an array of pointers to rectMD arrays. That's a strong construction because pointer to a rectMD array is completely defined. What it points to is not defined yet, but that's what you have new for. This exposes the weakness of strong construction, because if this is the only way of doing strong construction, then you have to make sure that when you're done, you delete. You have to make sure that you haven't, you know, handed off a pointer to someone else that expects it not to be deleted. There are lots of things that are dangerous about this. And that's why for these kinds of classes, we've gone largely with default and define for big things. And of course, you want to build things on unions of rectangles. I talked about that already. You can create aggregate data types for, it's a shadow world. You have box layout, which is boxes, unions of rectangles that are boxes. You have an iterator over all the boxes in a box layout, and then you have a collection of arrays that are defined on this union of rectangles. So you can build up a fairly elaborate class structure, and then you can use it for organizing yourself to do domain decomposition for parallelism. So what sorts of things do you come up with? I mean, it's easy to draw pictures of 5 boxes and make it look like it's going to be okay. But when you have a problem like this, where this is a 2D slice through a 3D collection of boxes, and these are not individual grid points. Each one of these are a box of several hundred grid points. So there's a lot of data here. The color coding in this particular case is distributed onto processors. Each different color represents a different processor. And now, how are you going to organize yourself to figure out who talks to what? Well, there are, you want to do it in a way that it's, you know, you haven't bought yourself a really big and ugly parallel sorting problem, or if you have, you actually solve it correctly. You want to do something that's no more than order log n per box. And in fact, even if it's log n per box, you don't want to do it any more often than you absolutely have to. So there are complications when you scale this up. So questions, comments on this? Okay, so I'm going to spend the rest of the lecture talking about GNU Make, which is our principal tool for managing the build process. So this is in green. It's the GNU.org site for where you find the GNU Make manual. And I emphasize this one here, this is such an easy read. This is one where if you're just learning how to use Make, you just keep a window open to this and find things as you need them. You have to know what to guess to look for. And that's, to some extent, that's what I'm going to try to communicate to you. But there's a lot here, and none of it is very hard. Because GNU is a fairly small language, as such things go. It's a tricky bit of script parsing to manipulate files specialized to work with compiling code. There are only 2 kinds of objects in a Make file. There are variables, lists of strings, and then there are rules, which are telling the, essentially lists of shell commands with a particular set of information that tells you what to do. There are only a few kinds of flow control. If not equal, else, and if. No forms or looping, no forms of looping available, no jumps, no recursions. This is very close. In its original form, it was a single assignment language. It was just, you define things once and that was it. And most of the difficulties, though, are there's a lot of meta characters in this, wildcards, regular expressions, things like that, that allow you to manage a lot of complication, but you have to get used to the notation. So here's a simple example of the two types of things in GNU Make. You have recursively expanded variables, things that are defined using an equal sign. So here I have three variables, foo, bar, and ug. Now, what do these three lines mean? So $bar or $anything says take what's in that variable and give me what it's defined to be. So foo is defined it to be whatever is in bar. Bar is defined to be whatever is ug is defined to be. And now ug is finally defined to be a string. So if here's my target all, and it just echoes whatever's, just echoes to the terminal whatever's in foo, $foo. And you type make all, and you get back, huh? And why is that? Because what make did is it built up the dependencies of all these recursively expanded variables and then expanded out these definitions, and finally found out that yes, indeed, foo is equal to the string huh. So what else about this? So in fact, what's going on in the background is that there's a table being built up of all these variables and who talks to what. Now, here's some things to keep in mind. Order doesn't matter for equals. Notice that ug didn't get defined until these guys were defined, didn't matter. Since this is just, you're only allowed to do single assignments with equal, this is completely unambiguous, independent of order. You can declare a variable as the composite of as many other variables as can be filled in by other parts of the make file. So here's an example you will see over and over again. You will have flags you want to pass to the compiler. Well, you'll make up a list of flags that are for debugging. There are a list of flags for optimizing. There are a list of flags for libraries. There are a list of flags for include files. And so then you'll build lists of these things using other GNU Make commands. And what it does is it manages the complexity of building up fairly complicated build scripts. And then finally, make also allows you to override everything else. So you may have dim equal 3 set somewhere in your make file and use it in the compile line. But then if you're dim equal 2, use it in the compile line. But you can actually override variables in the make file by saying, okay, when you invoke make, whatever it is you've defined for dim, replace it with this, replace it with 3. As originally defined, you couldn't append. This is an infinite loop. And the last declaration in a linear parsing, you kind of walk through it, and you may have multiple equals declarations, but it only pays attention to the last one. So as with all languages of this sort, single assignment languages, you find that it's just a little too restricting, so you introduce a little bit of kind of incrementalism in them. And these are so-called simply expanded variables. So you can You have two flavors of them, colon equals and plus equals. So rather than try to explain these words, let me just go down here and give you an example. So let's say I had C flags and I wanted to, I've already defined a bunch of compile flags, and now I want to add some more because I've realized that for the case I'm looking at, I want to have more of them. So I just say C flags, colon equal, $C flags, minus C, minus E, minus MMX. So it'll add this set of strings to the C flags list. And then another syntax for doing exactly the same thing is C flags plus equals minus C, minus E, minus MMX. And this is very specific to GNU Make. But life is a lot easier. Order does matter here, by the way. Once you've invoked colon equals, it matters that things are defined before use. So those are variables. Variables are just lists of strings. That's the way to think of them. And then rules are two things. Three things. There are targets. There's a name you give when you say make something, make a target. You have to give it a name. And then the two things you input to the target, one of them are prerequisites. What does this target need in order to build? And this is not actually all that smart. You have to tell it exactly what it needs. And the way it's using this information is that at the time when you're executing this target, one of the things it will do is it will check, have these changed since the last time I built this target? And do I have a rule for building one of these? If so, I will go back and build it. So it manages the fact that as things change, it will update to the latest version. So this is just the prerequisites part. Now, then the next line below, you will have a tab. This is one of those languages that has the annoying feature that tabs actually have meaning. So tab and then a recipe. So this is going to be call the compiler or call a preprocessor or something like that. And you can have multiple of these things. You can have tab recipe, another tab recipe, until you have a blank line. And that would be a rule. So here's a kind of simple example. Here's a build.o file, an object file. So clobber.o. You need a .cpp file. You need a .h file, and maybe you need some other .h file. And what is the rule? The rule is invoke the compiler, so tab, compiler, minus C, minus O. Minus O tells you output from the compiler goes into this object file, and then the last argument there is the actual thing that's being compiled. And you could have reversed the order of these. Now, you can also build an executable. clob.x, .ex, that's the target name. And by the way, these target names do not have to match anything over here. They're just a mnemonic for you to be able to type something in easily. So I could have said clobx without the dot for the target name. Would have worked equally well. Clobber.o, killerapp.o, those are the prerequisites. If they aren't up to date, or if they aren't current, or if they've changed since the last time you built this target, it will go and rebuild them if it can. And then tab, G++, output, you're outputting an executable, and these are the inputs, the .o files. So fine, this is a silly made-up example. Here's an example that actually is the example you're going to be handed to start with, or for the first programming assignment. So here's an actual make file, and we'll invoke make on this in a moment. I'm defining dim to be equal to 2. I'm defining actually a variable that's going to be my C++ compiler. And I gave it a name, CXX. And that's the string that I'm going to use for identifying C++ compiler. Why did I do that? Well, because I'm anticipating the idea that I'm going to be switching back and forth between running on Macs and running on Linux boxes. And Clang++ is the only compiler I've got on this particular Mac that will work. And C++ compiler. On the other hand, on Linux boxes, it's all G++. And maybe there's another C++ compiler, the GNU or the Intel C++ compiler. Lots of compilers around. you don't want to have to go through and find all the occurrences of whatever compiler you're using to just change these so you define it as a variable. So here is the name of my target, MD-array test. I gave it a nice mnemonic name. Here are the things that it depends on. Notice I have backslash and then new line, backslash new line. This is to not have lines that are infinitely long. This is all one line. By the way, if you put backslash space, make will be confused. So you have to backslash new line. So these are my dependencies. What does MD-array test depend on? Well, it depends on the main program, obviously. It depends on the things that I need for rectMD array. RectMD array, its implementation, box and point. Box has a CPP file. Point has an implem file. Point is not templated, so why an implem file? Turns out that one of the things I tried to do here is to encourage the compiler to inline as much of point as possible. And to do that, you have to actually, for the same reasons you would have to do it for templating, the compiler has to have the implementation right there in front of it to attempt to inline. So these are the things it depends on. So now, new line, tab, and what does the compile line look like? $CXX, so it will take whatever's in this and put it there, so it'll look like Clang++. And now I'm passing some information, minus ddim equals $dim. So dim is a variable that's defined in as a preprocessor variable in my source code, and I'm saying to the compiler, everywhere you see that, replace it with whatever is inside the variable dim. So now I'm using dim in 3 different ways, and they're distinct. There's dim inside of my source code. There is the variable name dim, and there is what it gets set to, which is actually 2. I have a couple of other compiler flags. This one here is to say use the C++ 11 standard. This is to allow you to add some debugging information. And now what am I actually compiling? mdarray.cpp, box.cpp, those are the only 2 compilable files. And then I'm outputting into mdarraytest.exe. So let's go look and see how this works. So, okay. Now I'll go over here. Open. Here's the GNU make file. So let me, I don't want to do that, it's not working. Okay, so here it's exactly what I typed here. Dim equal 2, CXX is equal Clang++, and mdarraytest is defined as defined here. Now, how do I invoke this? Turns out there's kind of a nice way to invoke it. This is all in Emacs, and Emacs has a tool, so you can invoke a compile line. What's going on down here? Down here it says, here's a compile command. Well, it's not the one I want, so let me just do make mdarraytest, and we're off. And in fact, here's the compilation output. Pops up in another screen. This is all Emacs magic, but it's good magic. And so it's popping up make mdarraytest, Clang++, and it's showing me explicitly what the compile line was. Great. And then I get an executable. Now I have a shell running here, and I can just go ahead and let's see. So all I've output here is, okay, tell me what the corners of my box were, just to make sure I was doing something correctly. So that was easy. There's one loose end here that I didn't say, which is when I typed make, when I typed compile. I could have typed this line down at the bottom in my shell. The one thing that this did was, by invoking the compiler here, Emacs went and said, are there any files that are up here that you haven't updated, that you have in the editor, in your Emacs editor, that you haven't written out to disk yet? Do you want to, in order to do this compile? And it gives you the choice, yes or no. So by invoking the compiler from here rather than from the shell, it does a little bit of checking if things are up to date. Now, notice I didn't specify a name of a makefile. The reason is that the first thing it looks for, if you type make, which is invoking gmake, it looks for something called GNU makefile. And that's its first choice, and we'll use that. And indeed, it does that just fine. So there are some more powerful rules we'd like to use. There are the two most important ones are pattern rules. So here's an example of a rule. So %o dot colon %o colon %.cpp. So what this does is it says, for every occurrence of something of the form %.o, look for something of the form %.cpp and do the following thing to it. So here is compiler -c, I'm just compiling, generating object files, and then with some flags. Now, how does it know what files you're specifically talking about? You want to do this for every occurrence of this pair. Well, the command is $, less than, is this guy here, is the source. And then it's doing -o output. $ampersand is the thing you're building. So this will take, so you'll see in a moment how this works. Every occurrence of something of .cpp and this pair .cpp and .o, it will run the compiler on and build a .o file. So this is so-called wildcard input, %.cpp, $ampersand is wildcard output, %.o. So this gets you a very long way. There is another set of things that you want, include and -include, which is to bring in more other definitions and rules. And when you start managing dependencies, this is essential. VPath is defining where to look for dependencies in make. So let's go over to another makefile. This is makefile number 2. First of all, one thing that you have to do, if you edit GNU makefile in Emacs, many Emacs's will recognize, oh, this is a makefile. And it will do all sorts of nice things with formatting. And one of the most important things is it will recognize tabs as tabs. For C++, the default setup that you want to use is don't use tabs as tabs. Have them replaced by some appropriate number of spaces, whatever you choose, but please do not use tabs. However, with makefiles, it's essential that the tabs be preserved because they have meaning. So this is the way you inform Emacs, oh, this is a makefile. Please treat it as such, because I didn't give it an obvious name. I called it makefile 2. Now, I have defined a variable called home, which is dot. It's my current directory. Makefile. I defined so this is the name of my file, but I've defined makefile to be makefile 2. I've made it a variable. Why is that? First of all, so I'll get to that in a minute. So let me just go down here. Dimension is 2. Now I have a bunch of flags. Here's C flags : equal minus standard equal C++11 minus G. C flags plus equal minus I dot. What is this doing? Well, this is C++. This is not make. This is not GNU. This is telling the C++ compiler, look for my include files in this directory. And the only directory I'm giving it is my home directory. I could have had a whole string of directories, and you'll see an example of at least 2 in the next example. C flags, now I'm saying, okay, here's how I want dim to be changed. I want it to, this tells the compiler to look for all occurrences of dim and replace it by $dim, which is 2. Now, I'm building up a list of source files. So here is $wildcard. This is another gmakeism. This is a way of building up lists. So it says, find all things of the form, in this particular case, home, / and anything that's of the form star C++, or star CPP. So wildcards work the same way as they do in shell. So this is the syntax for building up such a list. Here's another way of building up lists. It's pattern substitution. It's find everything of the form %C++ in this list in $source files, and replace it by %O. So that'll give me a list of things that of names for .O files that correspond to the names of .cpp files. Now here's my rule for making all of my .O files from all my .cpp files. Okay, this is compile -C, C flags, wildcard in, wildcard out. Now I've added a second rule here. $CXX -MM, C flags, $in, and then redirect. This is the shell redirect. Send it to another file. $star.d. So what's this? Well, this is a collection. This is going to generate a file or some text that'll be put in the file that has this name, star.d, where star was the original thing in front of .o. And it's going to be something that I can pull into the file, into my make file, that will define what all the dependencies are for that guy. And when you start trying to track down dependencies, you have to know what .h files have to be dependent, what other CPP files have to be dependent. This becomes essential in managing that, because each file may have a lot of dependencies. And this generates them automatically, sticks them in a file, so that down here I can include those files. And then we make MD array tests, and we're off to the races. And we generate. So now let's go back and look at what that looks like. So now I'm going to go to makefile 2. There's my makefile 2. It's just as I wrote up there. So now I want to invoke that. Let me invoke it, compile. Now I need to tell it that's the makefile I want to use. So here's how you do that in GNU Make, -f, makefile 2. Okay, so I'm going to do something else here because I didn't quite, I should have done something. So let me rm star.o. Star.o is fine. So I've gotten rid of all my .o files. So let me build again, compile. Good. Now it's, so since there are no .o files, it looked for them, it couldn't find them, so it went and made them. The way it knew to do that was because it had, in the dependency for MD array test, it had the list of object files. Can't find them? It looks for a rule to make each of them. And I had defined such a rule, so it invoked those rules. So let's go back up and look at the compilation. So for each .o file, it ran the compiler, and it ran it a second time to generate the dependency file, just to show you what a dependency file looks like. So dbox.o depends on CPP and depends on 3.h files. So it tracked down all the dependencies, and those can get sucked into your makefile the next time you invoke it. Those will get sucked in the next time you invoke it. Same thing for this power I to I. It turns out you don't get all the exponentials you need from CMath, so I added a couple that I needed. And then MD array recompiles, and then now it builds the executable. This is all linking, so it takes all of these .o files, links them together, generates an executable. Great. Now, one of the things I did was, so let's see how dependencies work. So what I'm going to do here is I will touch box.cpp. Touch is a Unix command. It says update the tag that says what its age is. So this thinks it's been updated. So now I compile again. What make did is it said, oh, box has been updated since the last time I invoked this. I need to rebuild box.o. Because box.cpp has been updated, and box.o depends on box.cpp. So it does that correctly. Now let me do something even trickier to explain another thing that I'm doing. Let's go back to makefile. Now I'm going to say, okay, I wanted to build a dimension equal 3 case. Let's see what happens. Recompiled everything. Why did it do that? It wasn't a miracle. It was not miraculously smart. It's that I did something smart. And what I did is that I put in all of my dependencies, I put the name of the makefile. So one of the things it will do, it will check the date stamp of the makefile to see if it's been changed. And if it has been changed, that means you have to remake everything. That's the way I've set it up. So when you're doing things like having dimension as a parameter, that's absolutely essential. Otherwise, you'll try linking 2- and 3-dimensional things together. You'll get into all kinds of trouble. So just to make sure that I got something sensible out of this, let's run it again. I think I can just do that. 64. Notice down here that it used 3 ints rather than 2. And fine. Wonderful. All right. Now, there's still one more example I want to go through. Let's go back to the lecture. Oh, include is a perfectly good statement in GNU make. Minus include is roughly the same statement. The difference between the two of them is that minus include does not complain if it can't find something. And why is this important? The reason is that the first time you invoke make, you will build the .d files, but they will not be available yet because they haven't been made to ingest. So the first time through the system, you kind of have to build twice to make sure you have all your dependencies available. So that, and the minus include says you don't want it to stop just because it can't find the dependencies. Now let's go on to makefile 3. Makefile 3, so I ran this program. It's a silly, it's doing something silly, which is it's telling me, yes, you made a box, but what does the solution look like? So in order for this to know what the solution looks like, I have to be able to plot it. And in order to plot it, I need to be able to use, to write it in a format that my visualization software can use. So where do I have that? Well, I have, here's home. I have utilities, which is in $home, and I have a subdirectory called utilities. And what I've done is I have in that subdirectory, utility subdirectory, I have a directory called visit writer. And so this writes out stuff that can be ingested by the visit visualization tool. So I have to include information about where visit is in 3 places, or the visit IO. One of them is in vpath. What vpath does is it says, where should I be looking to fulfill my dependencies? It has to, you give it a bunch of directories to look to meet its dependencies. So this is something you're communicating it to gmake. Here, this is something you're communicating to the compiler. What are you communicating to the compiler? You're saying, this is where you look to find the include files. -I blah is add this to the list of directories the compiler looks for to get include files. And then, of course, if there are any .cpp files, you have to include them in the list of source files because you have to actually compile them. So fine, I've now accounted correctly for having visit writer here. And now I have objects. So here's my objects.cpp.o. So pattern substitution, here's my build. Now I've done something a little bit tricky that can be helpful, is that I make my output file not mdarrayTest, mdarrayTest $dim d. So what that's going to do is that's going to put in front of, it's going to make an output file, say if dim is equal to 2, it'll be mdarrayTest 2d.exe. Oh, and there's one more thing I put in. This is going to generate an awful lot of files, and it's kind of nice to be able to clean up after yourself. So here's a target called clean. It removes executables, and it removes all the .d files and all the .o files. So let's see how. No, that's not what I wanted to do. So now let's go to, first of all, I have to turn back on something I turned off. So here is the header file for the thing that writes the data, that writes rectmdarray data. And here's the thing that actually calls the output routine. So I turn that back on again. So I commented it out before so I could look at the first two examples. Now I go to compile. And I'm now using makefile3. And before I do that, I don't want to, let me do a quick check. Makefile3. What I'm making sure is that this is 2D, because I don't want to try to visualize 3D on the fly. Okay, yes, indeed, it's 2D. Let's go back over here, down here, and hit return. No files need saving. Now, okay, so this turned out to be easier than I thought because Visit Writer had already been built. VisitWriter.o was already there. So let me make this a little harder. So let me do a make a -f makefile3. I think it was clean was the target. I think maybe it's real clean is the target. Yes. All right. Now let me make the build again. And as you can see, the compiler is looking in the right place for the visit writer. It looks in both places for the include files, always. Eventually, it does compile things in visit writer, a couple of .cpp files, gets the dependencies. Notice that the way I've set things up, the .o files end up in the directory that the .cpp file was in. There's a way of getting around that, but that requires more use of make. I'll give you a hint. There's a way of taking a make list, and it can tell the difference between something that's a directory string and a file, and it'll strip off all the directory strings. So there are various things you can do like that that will have all your .o files, say, end up in the directory that you're building in. Okay, fine. So I built this. Let's see if I can run it. Okay. Now, oh, what did I build? Here it is. mdarrayTest 2d.exe. So I have the dimensionality sitting there. I forgot to put the / in front of it. Okay, 64, 64. All right. So now I'm going to actually invoke visit. All right. Open. So let me look at, so I generated two files. One was of phi, one was of LFI. I open it. I add something, so this is pseudocolor. Draw. We'll go into a lot more detail on this on visit later. But again, it generated a nice file. Let me go and open the other one. So this is going to tell me something interesting. So add LFI, draw. Okay, so LFI and phi look for all the world to be almost identical. There's a little shifting there. Phi, though, has a range from -1 to 1, essentially, and LFI has a range from -78 to 78. So what's going on there? Why is this the right answer? Well, the right answer is that the product of signs I put in there is a discrete eigenfunction for LFI, and the eigenvalue is approximately 78, 78.8. So 8 pi squared. So this is just a tiny object lesson of something that you'll have more experience with later, of how visualization can be a very effective debugging tool. Okay, so any questions on this? So the plan is that by Thursday, we will have everything ready to go for assigning people. So here's the thing. I want to have everything ready to go for assigning people their Git repos by Thursday. At that point, I will also push out a bunch of stuff, the accumulation of examples and stuff I've been doing here. I think I will probably try to have, certainly either Thursday or the following Tuesday, have the first assignment ready to go. So I think that's it. Thanks. Yes, question? I think, okay, here's how I learned make, is that I have a make file and I know how to modify it. And so if you have a make file, you know how to modify it. You have my lecture today that gives you some idea of the range of possibilities. Have other things on the web as well, and then ask me if you get stuck. Yeah, you'll pretty quickly get good at make, because it's a very simple programming system, and it's really more a question of being able to follow the logic of a simple programming system than anything that's really all that subtle about it. So yeah, I think you'll be good at make. You'll certainly be acceptable at make simply by just copying by analogy what the examples you'll see. But I think you can get good at it pretty quickly. Excellent.